Okay, good day class. So today we are going to start a new chapter, which is chapter 5, Maclaurin series. Alright, so let's look at the analysis table. So Maclaurin series is a very popular topic in STPM. Okay, you can see that, of course, in part A, all the question 5 are related to Maclaurin series. And in part B, you see, so many years, they came out in part B, which is 50 marks. You see 2013, 2014, 15, 16. Okay, then they stop at 2017, then again 2018. All right, but since 2018 repeat paper, until 2020 repeat paper, this chapter not come out in did not come out in part B. All right, so you have to stand by. Most probably it will come out in part B this year, most probably lah. Okay, so you stand by. So make sure you master this topic. It is not a difficult topic, all right. So it's worth for you to master it. Okay, so now we see some introduction about Maclaurin series. All right, so we have discussed how binomial function can be expressed as a series of ascending power of x. Remember in Sem 1? So you have learned this one. Okay, 1 plus x to the power of n is equals to this. You remember this binomial function. This is a binomial function. And this function can be expressed as a series of ascending power of x. You see, the power for x is increasing. All right, by using the binomial theorem. And how the series can be used to find the approximate numerical values of certain irrational numbers, which you have done in Sem 1. So this binomial series is for all the n which is positive integer. So for this topic we are talking about n which is the positive integer. Alright, so there are a few more functions such as ex, ln 1 plus x, cos x, sin x, and etc. that can be expressed as infinite series by using Maclaurin's theorem. So binomial theorem express this function in a series. Alright, and Maclaurin's theorem can express all these functions in a series also. Okay, so this topic we are going to learn what is Maclaurin's theorem. Okay, we can use the Maclaurin series to find the approximation of definite integral, the value of a function, and the limit of a function. This is why we have to learn Maclaurin series. It's also used to find approximate value. Okay, like definite integral, remember integration? Integration where you have to sub in a and b. Definite integration. Means that we don't have to integrate, but we can use Maclaurin series to find the value. Alright, the value of a function, okay, means when x equals 1, what is f1, and the limit of the function. Alright, okay, and this Maclaurin's theorem was found by Colin Maclaurin, alright, which is a British mathematician born in 1688, alright, and until 1746. It's just like about 58 years. Okay, and by applying the Taylor series earlier founded by Brooke Taylor, means that this Maclaurin's theorem come from Taylor series, and this Taylor series is actually found by Brooke Taylor, which is from 1685 to 1731. Also a British mathematician. So Maclaurin, the Colin Maclaurin extend the Taylor series and become Maclaurin's theorem. Alright, so this is a bit about Maclaurin series. Alright, so before we go to Maclaurin series, first we must know one term, which is power series. We have to know what is power series. So representation of function as a power series. So this part we are going to discuss what is power series. Okay, an infinite series of the form means in ascending power of x, which is like this. We call this power series in x about c. Alright, in x about c, which can be expressed expand in this form. Alright, so let's see here. Can see, right? This is a power series. Alright, in x about c. This is a meaning. So this series is actually the summation. All right, this is a general term. So remember, in Sem 1 you have learned this is a general term, an x minus c power n. All right, so we are going to add all these terms from n equals 0 to infinity. So this is an infinite series. All right, so when n equals 0, so it's a0 x minus c to the power of 0, plus when n equals 1, so a1 x minus 1 power 1. When n equals 2, so a2 x minus c square plus dot 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 until infinity lah. All right, so we call this power series. Okay, in ascending power of x, so the power of x increasing, you see. All right, so this is a power series of x about c, we call it. Okay, so next step we simplify it. So x minus c power 0 1, no? All right, so left a naught, so we just simplify it into this form. All right, so power series. Okay, so we call this power series, and in x, we call it power series in x about c with coefficient an. This is the coefficient for each term. A0, A1, A2, the coefficient is an. All right, so this is the meaning of power series. Okay, so next, a special case about power series. It's a special case. Just now, c can be any number. Okay, so the special case is when c is equals 0. This is called special case of power series. So when c equals 0, so what will happen? Then the power series will become like this. Correct? Because c equals 0, so means that only x. So it's summation when n equals 0 until infinity for an xn. So when n equals 0, like this, n equals 1, n equals 3, n equals 2, n equals 3. Sorry, something missing, yeah? Okay, something missing here. A cube plus a cube, x cube. All right, and so on. Okay, so this is a special case of power series when c equals 0. So when we simplify it, it becomes like this. Okay, because x power 0 is 1 now. So after simplify, it becomes like this. Okay, sorry, I forget about my a3. Okay. All right, then we call this a power series in x about 0. All right, just now it's about c. So c can be any number, about 1, about 2, all right? And this is the special cases where this is a power series in x about x equals 0. All right? So power series in general, special case of power series when c equals 0. Okay, then next. Okay, next. What happened if the coefficient, if the coefficient is equals 1? Means that in this power series, an equals 1. So all the coefficient become 1. So when this happen, then the power series will become like this, right? So because an, the coefficient become 1, so left only terms xn, where n equals 0 to infinity. All right, so when n equals 0, this one, n equals 1, n equals 2, n equals 3, and so on. So after we simplify it, x to the power of 0 is 1. So it becomes this series. All right, so you see that the changes. So this is in general the power series in x about c. Then a special case of power series where c equals 0. So this is a power series in x about 0. And additional, if the coefficient of each term is 1, then now the power series become like this. All right, it's still power series because you see the power of x is increasing. All right, so this is then the power series become like this when and the coefficient become 1, and we call it, and you find that actually it is an geometry series, right? See, this is actually a geometry series with first term, this a is first term, not this a, okay? Where with the first term is 1, and the common ratio, so remember, common ratio is x. Means each term multiply x, you get this, multiply x, you get this, multiply x, you get this. All right, so from here you know that a geometry series is actually a power series also in special case. Okay, And since it is a geometry series, all right, since it is a geometry series, so remember the formula for geometry series? Okay, remember the formula for geometry series? Yeah, this one. All right. Okay. Since therefore you see that this power series, which is equals to 1 plus x squared plus it. So this, because this is infinity infinite or infinity. So this is, when I add up all the terms, it's actually sum to infinity. So remember, sum to infinity for a geometry series. And the formula for sum to infinity is a over 1 minus r. A is the first term, r is a common ratio. So we sub in our a and r. Okay, so remember a is 1, our common ratio r is x. All right, therefore this summation become this series, and this series can be simplified just in a function. See, this series can be just simplified in this function. All right, provided the modulus for x must be less than 1. Remember, geometry series, for this series to be valid, the modulus of the common ratio must be less than 1. All right, or x between -1 and 1. All right, so from this part, we can make a conclusion that, all right, this one. All right, so we can make a conclusion that 1 over 1 minus x is actually same as 1 plus x squared plus x cubed plus ... See? Okay, so remember, just now in our notes, we mentioned about this thing. All right, we mentioned about this thing. Series can be used to find a we may mention about this thing. Some functions, okay, can be expressed as infinite series. Remember this sentence? So we are actually showing you one example, okay, where a function can be expressed in a series. All right. So we will continue to your notes, page 2, number 5. Here, this one. We continue here. Okay. No pop-ups. Okay. All right. Just now the power of the light lost, so it's a bit dark. Okay. All right. So for this one, all this I have explained just now in the notes. So you see this example. All right. Just now we have explained up to here. Okay. So you see that. So this example where we express this one now, 1 over 1 minus x, this function can be expressed as a series. So this example shows that an infinite series in ascending power of x, where we call it power series, can be used to represent a certain function. All right. So in the other words, a function may be expanded as a power series in a single variable. So it means that some of the series, all right, can be expressed as an infinite series in one variable, which is x. All right. And number 6, we can replace a function with its power series expansion as long as the single variable x is small and within the interval convergency. Okay, so means that we can replace a function with with its power series expansion as long as the single variable x is small. Or means that after you get this series, you can sub any value of x inside here to find the value of this function. All right, remember that we say find the value of the function. This is the meaning. All right, as long as provided this value of x that you are going to sub in is in the range. There we call it interval of convergency. All right, this is interval of Okay, this is called interval of convergency. All right, means that the range of the value of the variable which you can sub into the series so that to make this series valid or to make it converge. All right. Okay, then next. So the interval of convergency of the series is a set of values of the single variable x for which the power series converge. It is, the expansion is valid. So it means that when we sub in the value, we can calculate the answer. All right. It is restriction on the values of the single variable in the power series so that the power series always converge. Converge means when you find the sum, when you find the sum of this infinite series, this value will become smaller and smaller and smaller until we can omit it. All right. And however, if the power series converge for all value of x, yes, there are some power series, no interval of convergency. Any value of x can be used. All right. So in that case, there is no restriction on the values of x. Okay. Later we will discuss some series which has no interval of convergency. Means any values of x can sub in, and the series is always valid. All right. And number 9, this is something extra. Okay, this is some extra information. We can use the ratio test to find the interval of convergency of a power series. Or maybe in some other series, we might know, what is the interval of convergency? Actually, we can use this ratio test to find the interval of convergency. All right, so this is the concept of ratio test. Okay, let's say the summation of un may be any series, this is any series. The series is convergent if this happen. The limit when n approach to positive infinity for un plus 1 over un. So this is 2 consecutive terms, remember? 2 consecutive terms. And this is actually what? This is actually your common ratio in geometry series, right? Okay, so if the limit for this r when n approach 0 must be always less than 1. Okay, this is a concept that we use. So when we sub in the values, we solve this one, then we can find the interval of convergency. All right, so this is just some extra information. So if you think you're interested, you can go online and search for it. All right. Okay, so we have done the concept of Maclaurin series. So we know what is power series. Because you need to know what is power series, then only we can go further to Maclaurin series. All right. So next, we are going to 5.1.2. So we are going to see Maclaurin series. All right. But remember just now we said, this Maclaurin series is actually, this Maclaurin series, okay, is actually applying the Taylor series. All right. So before we go to Maclaurin series, first we see what is Taylor series first. All right. So let's say, okay, f is a function, all right, that is infinitely differentiable at x equals c. Okay, so means that this function is a continuous function. So at any point of x, it can be differentiable, remember? Your f prime x axis. All right. Okay, your f prime axis. So let's say f is a function where it is infinitely differentiable at x equals c. That is the derivative f prime c axis for all positive integer of n. Of course, positive integer only lah. N means when you differentiate one time, then it's f prime now, 1 now. If you differentiate it again, then it become prime lah. Like 2 lah. Differentiate again, prime, like 3 lah. So this is the meaning of n, which is positive integer. All right. So let's say f is a function like this, where it can be infinitely differentiable at x equals c. So means that at any point of c, f prime axis, and this function can be continuously differentiated. You can find f prime, you can find f prime, second derivative, third derivative, fourth derivative, and so on. Okay. Let's say for a Taylor series concept, f must be a function like this first. Okay. So therefore the Taylor series for F about C is a power series. So Taylor series is also a power series. So just now we know what is power series already. Alright, so Taylor series is a power series where so Taylor series is also a power series, right? Where this happened. So remember just now we discussed about this power series in X about C. Alright, then when you expand it, it becomes A0, A1, X minus C, A2, X minus C squared, and so on, where your coefficient an must be in this form. Okay, for all the n. All n actually means positive integer n. Alright? So, this is power series. Why is so dark? Okay. Okay, so this is power series. Alright? So when this power series with this condition where the coefficient for each term must be in this form, which is the coefficient for the n term an must be in the form fnc, means we differentiate function f n time, or we differentiate function f n time over factorial n. Okay, so when this power series with this condition, then we call it Taylor series. Okay, this power series with this condition of the coefficient, then this one become Taylor series. Alright, and note that f0 is taken to mean that the function itself. Okay, means we never differentiate it, so it means it's the function itself. So you can see here. Alright, we never differentiate means f . Okay, alright. So this is Taylor series. So I will go further a bit for Taylor series before we go to Maclaurin series. Okay. So just now we have used the concept of power series and get this geometry series, right? Now we go to Maclaurin series, and before we go to Maclaurin series, okay, we will just now, like we say, we will see what is Taylor series. So f is a function which is differentiable at x equals c. Alright, means that f prime fnc exists. So means that you can differentiate f many times, yet it is exists. Alright, of course for n which is positive integer. Like when n equals 1 is f prime 0, when n equals 2, when n equals 3, when n equals 4, 5, and so on. So all this must be exist. Alright, therefore Taylor series is a power series where the coefficient of each term is in the form fnc over factorial n. Okay, like what we have discussed just now, I just repeat. Okay, and this is something extra. Remember, if n equals 0, okay, if n equals 0, then it means the function itself. Okay, therefore the coefficient a0 will be f0c. C must be in bracket. Okay, and 0 factorial. Alright, 0 factorial is 1. Again, you have learned in Sem 1. 0 factorial is 1. Therefore, the coefficient of the first term is fc itself. Means just sub c into the function. Alright, so this is Taylor series. Okay, therefore we can make a conclusion that Taylor series is a power series for f about c. Why about c? Because it is in the form an summation of an x minus c power n. So it's about c, where an must be fnc over factorial n. Alright, therefore this power series, remember just now at the beginning we have learned, so therefore this power series now become, this is a power series that we already simplified just now, right? Okay, so by substituting this coefficient, So it become, just now we explained already, the A0 is FC, we already explained here, all right? And A1 is F prime C, A2 is F prime prime C 2 factorial, all right? Maybe we add one more A3, maybe we add, let's see, okay, maybe we add one more, 3, so that you can see clearer. So 3, the coefficient will be F prime prime C over factorial 3 x minus C cube, alright, plus dot dot dot. Yes, this is Taylor series for F about C. Okay, alright, so after we have Taylor series, then what is the relation between Taylor series and Maclaurin series? Okay, here we are. Yes, just now we already said. Okay, like this easier. Okay, all right. So just now we already said a Taylor series is a power series of for F about C. So it becomes like this. Therefore, the Maclaurin series is a Taylor series. It's a Taylor series for F about 0. So about 0 means all the C become 0. Alright? Then it become like this. Okay? We compare again. Okay, this one can take out already. So we compare again. Yes. This is Taylor series of F in F about C. And Maclaurin series is a Taylor series where C is equal 0. About 0. About 0. So means C equals 0. Then this is the Maclaurin series. Okay? So the summation of AN XN, because C equals 0, so no more C. So FC, C equals 0 must become F0, F prime 0 X, F prime prime 0 factorial 2 X squared, F prime prime 0 factorial 3 X cubed, and so on. Okay? Alright, so I hope you have the concept. First, we start with power series, where it is any series, Okay, we start with power series, where it's a series in terms of X with the power of X increasing. Alright, then from power series, we go to Taylor series with the concept, the coefficient must be equals to FNC over factorial N. Alright, where Maclaurin series is a Taylor series where C equals 0. Okay, so this is what we call Maclaurin's series. Alright, so later we are going to use this Maclaurin series to find the series of some function. Alright, so remember, for Maclaurin series, okay, your coefficient AN must be Fn 0. Everything go to 0 already with factorial N. If Taylor series is more complicated because you have C here. The C can be anything. So Maclaurin make it simpler. So make it C equals 0, then it become a new, not new series lah. It become a standard series where you can use its name, Maclaurin series. Okay? So now you know what is Maclaurin series. We will continue some further. We will continue some further information about Maclaurin series. So we will go back to your notes, page 3, and we continue number 3. Alright, here. So after we have explained how to get this Maclaurin series, here are some important things about Maclaurin series that you must know lah. Okay? So this is Maclaurin series. This is Maclaurin this is Maclaurin series. Alright? And now we have to see what is Maclaurin's theorem. The steps, the concept, and the steps that we use, okay, by using this Maclaurin series to form the series of a function. We call this Maclaurin's theorem. This is series. Theorem is a steps, or it's a set of steps that we have to go through so that we can get the series of any function. So we call it Maclaurin's theorem. Okay, so Maclaurin's theorem say that first, let f be the function that can be expressed as a power series in x. First thing, the function must be something that can express as power series. It is this one now, as we say earlier, where x is a variable and an are the coefficient to be determined. Then fx can be differentiated terms by terms. Alright, this fx must be something that we can differentiate until the n fn. Alright, and it must be exist for all positive integer of n. Means when we sub 0 into all level of differentiation, it must be exist. So to use this Maclaurin series, actually one important assumption that we must make is, remember this, one important assumption that we must make in deriving Maclaurin series is this one. Because we are, just how we say, right, it must be a function that can be differentiated many times. Alright, means that like this, this series must be something that you can differentiate many times. So the assumption that we are going to make will be, we can take this summation out. Alright, so differentiate the summation of an xn same as the summation of differentiate an xn. Means we differentiate an xn where n increase, then we add them. It will be similar to this. This is the assumption that we must use. Then only we can use this Maclaurin series. Alright? And second step, this is the concept, first step. It must be happen. Then second step, since we already know that the function can be expressed as a series, right? Then we sub all the 0 in. We sub x equals 0 into the function. Then we differentiate it and get f prime x. Then we sub 0 into the f prime x to get our a1. Then we differentiate f prime x again to get f prime x. Alright, then we sub 0 into the f prime x to get our coefficient of the third term, which is f prime 0 over factorial 2. F prime 0, this value is to use here. Then differentiate f prime x again, we get f prime x, the third derivative function. Differentiation you can check yourself. Then we sub 0 into the f prime x to get the coefficient of the a3. Alright, so you repeat all this step until some terms. Okay, maybe you will think, then how many terms we have to express? It depends. Normally in the exam, they will tell you in the question. They will tell you in the question how many terms you must use. Alright? And here, the last one. By performing further differentiation and substitute x with 0 into it. Hence, the power series of the function in the power series form will become like this. Alright, so this is any function like 1 over 1 minus x, whatever, can be expressed in the series by using this formula. Okay, so we call all the steps that we are going through just now, all these steps that we are going through just now, as Maclaurin's theorem. And the series, we name it Maclaurin's series of the function f. Okay, so I hope until here you are clear what is Maclaurin series. Okay, if fx is undefined at x equals 0, so let's say fx undefined. When you sub x 0, then f undefined. Or for example, this is a function. You cannot find 1 over 0, right? Then fx cannot be expressed as a Maclaurin series. So Maclaurin series, not all function can be expressed in the series form. Okay, so this is one of the example. This is some examples where this function cannot express in a series by using Maclaurin series. Because when you submit 0 into the function, all are undefined. Okay, so this is an important thing. So please memorize it. Number 5. So in general, the Maclaurin series can only be determined if, so these 3 conditions must have, then only we can use Maclaurin series. First, the n derivative of fx must be exist. N derivative of fx must be exist. Means f prime x, f prime x, f prime x, all must be exist. And B, Fn0 is defined. Means when you already have all these derivative, then you can sub in 0 into all these derivative and you must get the answer. Oh, cannot be like this lah. And the third one, the series obtained converge to Fx. Okay, the series obtained must be converged. Okay, all right, so this video I will stop here first. Okay, so you try to understand the concept. All right, then the next video I will start discuss standard Maclaurin series and how to use Maclaurin's theorem to find the series. All right, so see you in the next video. Okay, bye.